Tariq is at CHERITech. He's chief architect there, and he's been leading a couple of different things, but I think particularly important to us is the standardization effort around Cherry RISC-V. He's really been a driving force behind helping to make that happen, but also working with their microarchitecture teams and so on to build, which I guess is probably like the first commercial quality product Cherry RISC-V for a reasonable scale, like an MMU-enabled application for, which is really exciting. We're just immensely pleased to see that happen because the kind of software stacks I've been showing you are the kind of things that we want to run on that. So I'll maybe just hand over to you and take questions in due course. Thanks.
Okay, thanks. Hi, everyone. Yeah, I'm Tariq. I'm CHERITech. I live in Bristol in the UK. So I've been involved in Cherry actually for about 3 years, 2 years for my current employer, and then 1 year when I was working for Huawei before. So I was helping out with trying to get sort of Cambridge University involved with RISC-V so we could talk without having to cross the trade ban in my old existence. Obviously, that's not a problem anymore. So I've been involved since Cherry V8 and saw the transition into Cherry V9. So a few things changed. For example, Cherry RISC-V became the base architecture, moving on from Cherry MIPS, and the future ideas such as Cherry x86 were added. And Cherry RISC-V actually changed a fair amount in Cherry V9 as well. So it was the merged register file only. There's no more split option. JLR.mode. What do we call it? Okay, yeah. So a few changes in Cherry V9, such as the mode-specific jump, and which we subsequently removed, DDC, PCC offsetting, and capability inspection instructions like get high and then set high to set it up so it's easier to load a capability from memory and such like. Per privilege enables and various other things changed there. On keyboard, that one. Yep. So so sort of in the background, CHERITech, we were working to fill in the gaps in the written documents. So I think a fair amount of the spec was just in the sale model. We were trying to turn it into something written down, which we could actually use for design and implementation teams. And there was some things which weren't clearly specified. For example, most instructions in capability mode had a C added, but did C.J also have a C? Because actually the semantics didn't change in capability mode. So we were trying to fill in all those gaps. There was nothing in there at all for debug. So SDX, SDTrig being the standard RISC-V extension. So we defined something for that. And merge and exception priorities was an important one. And so on and so on. And so we put all that together. We built a Linux-capable Cherry core, which we demonstrated at the last RISC-V summit with a lovely picture of Carl, who's here somewhere. I can't see him. Oh, he's waving, he's up there. So we showed that off on our A730 core, dual issue in order, Linux capable. And not fake demo, it was a real demo, and showing off detecting a buffer overrun, sorry, on the stack, and showing that it was better than stack canary because it trapped synchronously instead of waiting for function return. I'm sure Carl will tell you more about that during the break if you're interested. He looks like that. And so we started working with Cambridge University on the spec more or less since sort of getting to know each other at the Barcelona RISC-V summit last summer. And actually, I think it's still the case. If I email Robert, the email goes to spam, and if you email me, the email still goes to spam. So for a while, it was quite difficult to get that going because emails were just disappearing. But we got there, actually through me having Alexandra's phone number. was the way through that one, as Google were thwarting us in both directions. But okay, so yeah, so by that point, we'd actually started working on a different version of the spec document. And so what we were trying to do was take the more mature features from the Cherry V9 spec. The Cherry V9 spec's enormous. It has all kinds of things in, some mature, some more experimental. So we were trying to find, the more mature features, obviously the spatial safety being the primary one, and define something stable enough, fill in all the gaps, make sure we could actually build it. And that's what we did. We wrote it as an implementation spec, as I said before, and covered everything the implementation and verification teams needed to know. And then we put that onto GitHub. That was about the start of this year, I think. And that became version 0.7 as the first release. So that just went in as one enormous pull request. Sort of several 100-page pull request. And we officially got the TG formed in 2024, but we still have no chair and co-chair. Is that true?
We think we can share it.
Oh, but not confirmed? Okay. But, and since then, we've been working on really refining it and making improvements, simplifying it, trying to make it easier for RISC-V adoption. So, for example, actually, maybe I'll say on the next slide, getting rid of the duplicate mnemonics made a big difference, I think. So I said a few examples of things we've been working on the next few slides. So I think probably the biggest one was the RV32 format. So RV64 has a lot of encoding space, it's not a problem. But RV32, the precision wasn't good enough, and it basically needs to be improved. So if we studied what was in the capability format, we had 12 bits of permissions, which is a lot out of 32 bits. 8-bit mantissa, which was a bit too short, so we didn't get enough precision. A bit for the flag, which is the mode, capability mode, or it was integer mode. We renamed it legacy because it makes more sense. It had an object type, the O type, and the internal exponent flag. So it's a lot of permission bits. We decided not to use the O type for the time being. It may come back. The mantissa is too short, as it says. Mode is only relevant when your capability is executable, so you don't need a bit for it all the time. So data capabilities don't need a mode bit. So that was a waste. We wanted some space for future expansion, and we wanted some software-defined permissions as well. So we spent a considerable amount of time reworking the format. So starting with the permissions, I've sort of ordered them by what we did with them. So access system registers is still there, called ASR as an abbreviation. Store and load are still there, but as write and read, W and R. Execute, of course, is still there. So the store cap and load cap were combined into a single one, and then you also have read or write in there to say which one. So you can't load and store cap. You have to, it has to be symmetrical. You either have cap permission or you don't. Store local cap, we are expecting a pull request for the local global support pretty soon. I don't think it's there yet. And which covers the next two permissions. There are some that we've deferred for the time being. So the compartment ID, sealing and unsealing, and CInvoke, we don't currently have. So we wanted to keep 6 permission bits, and we've encoded them into 5. This table is actually out of date as of Monday, because Alex Richardson's put the load mutable pull request in, which adds two more entries to it. So it's dynamically changing, but improving. So what can we say? So we've got 6 bits, we've got encoded into 5, and we split it up into quadrants. So I don't have a pointer, but quadrant 1 with all the ticks in is the executable region. And so you can only execute capabilities in quadrant 1. So in quadrant 1, you have the mode bit. And because that's only 1 bit in a quarter, so 1 quadrant, that's only a quarter of a bit overall. So that saves 3/4 of a bit, which is very useful. And the bottom quadrant, you've got capability permission, and the top quadrant, you haven't. And the idea is anything in the bottom quadrant, it says reserved bits for future extensions must be 1, so they're implicitly granted. So we can add more controls to the bottom quadrant, which are currently already there. But for the top quadrant, all missing bits are implicitly 0. So if you add more controls, they're implicitly off. And expansion room, we've allocated, we've got 19 left, well, actually, which has just gone down to 17. So we've got about half of it still to go. So we have a new format. So we have 2 software defined permissions, SDP, 5 architectural permissions, and including the mode bit, so it's 6 bits encoded into 5 with free space, as I just said. 4 reserve bits, which we're likely to use for a local global scheme, hopefully quite soon. 1 bit for sealing, and the standard, the normal bottom and top, and the bits of the exponent, and the extra T8 bit, which gives us an extra mantissa bit when the exponent is 0 for better precision. So another thing we had to sort out was AUIPC and JALR. So in theory, well, actually, I think it was demonstrated that if you use AUIPC and JALR to go to any arbitrary address in the address map, there were some cases where the intermediate address could be unrepresentable, even though the final one was representable. So you could sort of jump out and then jump back in, meaning that linker relaxation would fail. So we had to rework the format for that. So part of the solution was to increase the mantissa length, which we wanted to do for precision, better precision anyway. But also we changed the definition of the representable range, so it was more accurately centered on the bounds. And I think that took a long time to get through, but Peter did prove it. He's here somewhere, I'm sure. And we're happy with the result, and it's merged. Pull request is merged, and RV64 has the same scheme. So the upshot of that is the representable range definition changed fairly recently. Illegal address handling was actually the hardest of all, I think, of all the things we've had to put up with. So the problem is that if you're implementing 39 or 48 bits virtual memory in RISC-V, all the upper bits must match with the address, and you don't have to store those upper bits. So you can choose for all your address registers, which obviously includes the PC, and the PC goes everywhere. You can choose not to store the upper bits, which saves considerable area. And RISC-V says that you can convert any invalid address into any other invalid address, providing they're both invalid, then it's fine. They're just, because as soon as you use it, you'll get an exception. So it says there, if the upper bits 63 to 39 for SV39 don't match, then the address is invalid. So what we can do is we can store 39 bits and a bit to say it's invalid. So the problem is that we've compressed an address and we expand it again, so obviously we've lost information. And the problem is that if you have a capability and you've changed its address, then you don't really know what it means anymore, especially as the leading one can change. If it's still tagged, then it could mean something unexpected, which caused us a big problem. It says that a new address might be unrepresentable, meaning replacing the address without specific checks might cause a tagged capability with unexpected properties. So it could be that the address was in bounds before, but we've changed it, so now it's out of bounds. It could be the opposite. It could be that the address has become unrepresentable. We have all these different cases, and you say, well, okay, whenever I'm reducing an address, so it's load store and installing a PC when you're jumping to it, what you really don't want to be doing is putting expensive hardware in place to see what's happened to your capability when you've modified it. All you want to know is that whether you can still use it or not, because if it's invalid, it's guaranteed to cause an exception. What you're trying to avoid is a sort of an intermediate, putting expensive hardware in to create an intermediate capability, which is guaranteed to be safe. So what we ended up doing was saying, well, if it's a legacy core, then it must take an instruction access fault or load store access fault, depending. So if the capability bounds are infinite, then we know that whatever happens to the address, we're not going to have a problem. So if the bounds are infinite, we just leave it as it is, and it's fine. If the bounds aren't infinite, we know we're running Cherry software, and then we just say, I've got an invalid address, and just take a Cherry exception at that point, which means that there's now no advantage in having bounds in the invalid space at all, because you can never successfully dereference, which means that we can make the comparators smaller. So for when we're doing bounds checks, so for SV39, we only need 39-bit comparators, whereas previously you needed full 64-bit comparators. And if you're issuing multiple loads and stores in parallel, that's quite a big saving. That was months of work, summarized in 2 minutes. But we got there. Other things that we changed to try and make the adoption easier. So originally, Cherry had separate SCRs, as in special CSRs, but we got rid of those and we merged them into the same space. For a while, we're using aliases, so we had more than one address, but we combined them so that if you access MTVEC in legacy mode, you get MTVEC, and if you're in capability mode, you get the MTVEC-C, which is the capability version, but at the same address. We got rid of the duplicate mnemonics, so CJAL-R is now JAL-R, CLC is now LC in all cases, easier for the assembly writer, easier to understand. And easy mode switching, so we put the mode switch instruction in. So certainly Morello and some of the versions of Cherry RISC-V have instructions where you can operate in the other mode, okay, which takes a lot of encoding space. So we thought it was easier just to quickly switch, and then you can operate in the other mode and then switch back again, which makes life easier. And trying to remove instructions which could be emulated with short sequences of other instructions to come up with a sensible base. So colorful list of extensions that we proposed. The green ones are stable now. So we have pure cap. So your base is always a pure cap machine. Legacy is adding in the legacy mode support with the old integer mode. The next one is byte half, load, reserve, store conditional. None of these are official RISC-V names, they're just what we've called them. France has recently merged the secure thread ID for compartmentalization, or C18N, as it's otherwise known. We have the PTE extension, where the challenge there is not to use up too many of the reserved bits in PTE for revocation, which we were discussing yesterday. And then we have a whole list of other things we'd like to add, which I've listed in red, which we've done no real work on. And so what we'd like to get to, so at the moment we have an RVA22 core, which supports Cherry and CODA-SIP. We'd like to get to an RVA23, which has a couple of big challenges in there. There's the combination of Vector and Cherry, where we'll have to check every byte of every load and store, every unmasked byte of every load and store against the bounds, which may well be complicated in some cases. And Vector and Hypervisor, where we'll use Morello as a reference, but haven't looked into that at all. And, oh yeah, code size reduction quickly, because I chaired code size reduction in RISC-V, so I like to add it. So table jump, ZCMT, we've already put in, and we've got some ideas for how push and pop can work as well. They don't change very much, it's just that the data type is doubled in size. So your registers are doubling in size. And that's it. So the world domination bit's the most important. That was your phrase.
I think there's even time for a question. If there is, probably 2 questions. Oh yeah, sorry. Of the changes we've made, how micro-architecturally dependent are they? I think they should all be independent. Generally, we're trying to simplify. I don't think we've done anything specifically based on our microarchitecture. And if we have, it wasn't the intention. Okay, any more? Well, you certainly need access to an almighty cap in debug mode. It's all written up. You can see it's on that link there.
we done?
Okay.
Stunned silence.
Thank you
Must
very
have been
much.
good.